So today we're going to look at the mechanism of free radical CH substitution. So that's taking a CH bond and making a halogen. So we'll see exactly how for methane and chlorine, how that happens. And then we're going to look at the thermodynamics for each step of the mechanism. And so once we do that, we're going to look at all of the different halogens, so F2, CL2, Br2, and I2. We'll find that the thermodynamics really only allow for chlorine and bromine to proceed. And then the later half of the lecture, we're going to look at the individual primary, secondary, and tertiary hydrogens to understand the reason why tertiary hydrogens will react more selectively than secondary or primary. And again, that all relates back to the thermodynamics of the making and breaking of bonds. So we left off last time on this slide where we saw that using the uniqueness sets, we could then predict the number of monohalogenated derivatives that were possible. And so given the carbon count, the alkane name formula, we already know how to determine the uniqueness sets of H. And so really we're looking at that set number for H. And then we can further classify the different types of CH as methyl, which is primary, methylene, which is secondary, or methine, which is tertiary. And then for the mono-substituted products, we can see the total number here, 1, that matches that 1 number there. 1 matches 1, 2 matches the 2 unique sets. So each unique type can get substituted for halogen. And then when we get up to butane, we see that butane had 2 unique sets, but overall it gave 3 total products, and that's because when we substitute at the secondary position, we can generate stereoisomers. And so that is going to speak to the mechanism of as well. When the radical forms, the hybridization changes, and then it gets substituted on either lobe of the p orbital. So that will generate a stereogenic carbon. So that's why there's a discrepancy between this 2 unique sets and 3 total products. So that's something you have to look out for is once you do the substitution, you have to ask the question, did I generate a stereocenter or not? So we're going to start by looking at the mechanism of the reaction of methane plus chlorine doing a CH substitution to make chloromethane and HCl. So when I talk about mechanism, really what we want to focus on is arrow pushing to account for electron movement. So that helps us understand how bonds are broken and made. In the free radical mechanisms, so this is 1 electron moving, and then we indicate that with a fishhook arrow. So the arrow only has sort of one side, that fishhook, that indicates a single electron is moving. So we need to account for how do we break a CH bond in methane, and then how do we make the CCl bond in chloromethane. So it says chain mechanism. What that means, there's going to be an intermediate in here that gets recycled, and it forms a chain reaction that keeps going until it terminates. So there's 3 different steps that are unique So I'll write step. So the first step is called initiation. And what happens here is the chlorine-chlorine bond is the weakest. So I'll have another slide where I put some numbers in to these, but right now I just want to show the arrow pushing. So that can be initiated with heat. I'm gonna designate as the Greek delta heat. So alternatively, or you can use light. And so that's going to cleave that sigma bond. So we know that a sigma bond has 2 electrons. Each chlorine is going to get 1 of them. So that generates 2 chlorine radicals. Keep in mind that the chlorine still has its 3 lone pairs. So overall, if you calculate the formal charge, the chlorine is neutral. So it has no charge on it. So that's one type of step. The next step is called propagation. So the chlorine radical, I'm not going to draw the lone pairs. I'm just going to show the movement of the important electron, the radical. The chlorine radical is going to abstract a hydrogen from methane. So that radical moves. We cleave that CH bond, so that forms HCl, and then a carbon radical. So that's propagation step 1. And so now we have this, so let me just say radical, and I'm going to use this term reactive intermediate. So by reactive intermediate, I'm saying it wants to do something to become a stable product. So in propagation step 2, it's going to react with chlorine. So it'll form a CCl bond and then a chlorine radical. So this is the chain part of it. So let me highlight in green here. That chlorine radical will then go back up into the propagation step 1 and then react with a molecule of methane. So that's the chain part. It's like a circle. So we would call this the propagating radical. So that's the ideal situation, because now you're forming the HCl in the first step and then the chloromethane in the second step. But that doesn't always happen because these things are reactive. They're going to do other things. So there's other steps. The third type of step is called termination. You can have a lot of different types of terminating steps, and it's basically when two radicals react with one another. So for example, if we had the methyl radical react with the chlorine radical, so we can just bond those together. That forms the product chloromethane, but notice that there's no other radical produced. So when those two combine, it stops. Alternatively, if you had two methyl radicals find one another, I'll call that termination A, termination B. So two methyl radicals collide, they would form now ethane. There's no other radical produced, so the chain is terminated. Another type we could imagine is just the two chlorine radicals combining back to one another. And so what you'll notice why these reactions can get complicated so I'll highlight in blue here. Say that, this termination step forms ethane. Well, now you have a second hydrocarbon in there with methane. And so the ethane is perfectly fine entering the chain as well. So that could go on. To form chloroethane. And so now you would get a mixture of chloromethane, chloroethane, and you'd be tasked with separating them. So the fundamentals of the chain reaction are shown there, but just keep in mind you can have these other things happening that will produce mixtures that are hard to separate. So really in the design of these reactions, we have to know what's the most appropriate halogen to use, and then where is it going to substitute, a primary, a secondary, or a tertiary position. So in the rational design of this, as we look at these numbers, it allows us to predict what the major product of a reaction is going to be. And so all of this stuff is linked. As I said, we're taking hydrocarbons, which come from petroleum. We're adding halogens. And then later on in this module, we're going to learn how to substitute those halogens for other functional groups. But we want to do it in a very rational way. Any questions before we start looking at the numbers for each step? So on this slide, all I've done is I've taken those different types of steps, so initiation, propagation, and termination, and written them in a table format. And then the last column, all I'm going to do is look at the bond association energy tables, and we'll fill in some numbers. So in the initiation step, when we look at cleaving a chlorine bond, so because we're breaking a bond, we have to add energy. So this number is going to be plus, and then that value is 243 kilojoules per mole. So that's right from that table. So now in the propagation step 1, notice there's two things happening. We're breaking a CH bond of methane. So that requires 440 kilojoules per mole. And then we're making the HCl bond. So when we make, we release energy, so that's negative 432. And so we have two numbers there and we just add them together. So overall that's going to be plus 8. So the initiation step, we got to put some energy in to cleave that CCl bond. Then we're in propagation step 1. Overall, that requires plus 8 kilojoules per mole. Now, if we look at propagation step 2, we're breaking the CCl bond. So we found that that was plus 243. And now we're making the CCl bond in methane. So that's going to release negative 352. Now for that line, when we add those numbers together, it ends up being negative. So negative 109 kilojoules per mole. So what's the important thing to note about this? So we said that radical, the chlorine radical, was propagating. So it's going to go back up here into propagation step 1. So when we look at this number, negative 109, we ask the question, is that producing enough heat or energy to meet the requirements of that step? So we know that negative is releasing heat. It's releasing 109 kilojoules per mole. The prior propagation step takes plus 8 kilojoules per mole. So the negative 109 greatly exceeds that. So if you do the math, if you take 109 divided by 8, so it's approximately 14 times the amount of energy is being released in propagation step 2 to carry the radical back to propagation step 1. So that tells you that the radical chain is sufficient to keep going, to sustain itself. When you look at the termination steps, because you have bonds forming, all of those energies are negative, and you can just look at the table to find the values. So this one's negative 352 to form ethane. Now that's forming a carbon-carbon bond, so that's negative 378. And then we saw to form chlorine, it's just the opposite, negative 243. Those generate heat, but again, they don't propagate the reaction cycle. So this is when we're using chlorine as the halogen. If we change this out and do the exact same analysis for fluorine, bromine, and iodine, these values have to change because you're forming the different hydrohalic acids and the different halomethanes. So you'll get different values in propagation steps 1 and 2. And then we have to combine them to see if it's actually going to be self-sustaining. So chlorine's a good molecular halogen to use for this. One issue is that in terms of reaction design, you really want these to be kind of closer together and not generate so much heat. Because again, when we're looking at primary versus secondary versus tertiary CH bonds, remember they all had different values. So again, that's the table. You can find that in your textbook or just use this slide on the exams as you need it. So here's the slide with the numbers in, and the green, again, to reiterate, the green value is showing you that you do produce enough heat to meet the value from that step. These red ones are terminations. Notice there's no other radical formed here. So in this slide, what it's doing is just summarizing the different halogens. So F2, CL2, Br2, and I2. We've run through this scenario with chlorine. And then we can use the table to fill in these other values. And then what we're going to do is really compare the propagation step 1 and 2 entry values to see if it's feasible to use these other halogens. So the numbers are in the table. I would encourage you to go back and do that yourself to see if you come up with these values. So again, in the initiation step, really what you're looking for you're just getting that value straight away from the table of cleaving that molecular halogen bond. That's where those numbers in the first row come from. The second row, remember, you're breaking a bond, and then you're making a bond, and so what changes is your value of X. So you're looking up for that first column, F in particular. So those values all change depending on the halogen. And then the third row, again, how is the methyl radical cleaving the X2 bond and then forming the CX bond. So let's take a look at, we'll go through these one by one. So let's look at fluorine first. So propagation step 1 is exothermic. So it's producing energy. Propagation step 2 is also producing energy. So it's producing a lot, more than that value just in terms of the magnitude. So both of these are negative. So what ends up happening when you use F2 is that it's very non-selective. It's going to just substitute any CH that it sees. And again, we really don't want that. We want to control what's happening. So there's actually too much energy being produced with fluorine. For chlorine, as we said, the negative 109 is enough to meet the +8 required. It's about 13 point something times as much, but it still meets that demand. The bromine propagation step is endothermic by +74. Propagation step 2 is exothermic by -100. So those are really well matched. You have just enough plus a little excess to meet the propagating step. And then we see for iodine, it actually inverts. Iodine propagation step 1 is now +142. And then propagation step 2 is now negative 89. So even though that's exothermic, it does not meet the energy requirement to propagate the chain. So in essence, fluorine and iodine are out. So it's the Goldilocks scenario here. The porridge is too cold, it's too hot, sort of thing. So we're going to focus on chlorine and bromine. And then within that, there's two things that we're going to talk about why they're different. And so we'll look at these energy curves based on those numbers. It's another way of just looking at what are the numbers telling us. So because that number 109 for chlorine, it exceeds that, we say chlorine is promiscuous. And what I mean by that is you have a choice, primary, secondary, tertiary. No matter what, chlorine can substitute any of those. It's not very selective. Bromine, since it's better matched, it's chaste, it's not very promiscuous. It's going to go after specific types of hydrogens. So it's more selective in how it reacts. And that's really what we want when we're designing reactions, is to be very rational about what site something is happening at. So we'll look at the reaction coordinates just as a visual representation of why chlorine is not as good as bromine in terms of selecting. Any questions? So the way we're going to do this, we'll look at propane under chlorination and bromination conditions. So we have primary and secondary hydrogens in propane. We're going to do that ratio thing. What ratio would you expect just based on statistics? And then we'll look at what are some actual yields that will help us understand why there's this selectivity in terms of the type of hydrogen. So there's our propane. And if we say number of each and then we classify primary, secondary, tertiary, we get a total, and then we can just convert that into a percent. That would sort of be our expected theoretical yield for substitution. So those are primary hydrogens. They're equivalent, so we would say there's 6 of them. Secondary is a different type of set, so there's 2 of them, and there's no tertiary. So that gets us a total of 8. And then all we're going to do is take the number in that row divided by the total and to get us the percent. So we have 6 over 8 and then 2 over 8. So that's going to get us 75, 25, 0 in our total 100%. So in theory, when you do these type of substitutions, your expectation would be the primary product would be present in 75%, the secondary substituted product present in 25%. But we're going to see that's not the case. And again, it has to do with the different bond strengths, CH bond strengths of primary versus secondary versus tertiary. So in terms of types of each present, We said primary was 6, so that eliminates C. Secondary was 2, that eliminates D. And then tertiary was 0, that eliminates A. So B gets us our correct response. So based on that, we would expect the theoretical yield to be 75-25. So that's C. So let me just, do I have it on here? Yeah, so the important thing is right there. That's the prediction, just based on the theoretical analysis. But what are the actual yields? And we can do some empirical type of math that's going to show us that secondaries are more reactive than primaries. So let's run through the logic of this table. So the first column is talking about type. The second column is when we're substituting a primary hydrogen for a halogen. And in this case, we're specifically looking at chlorine, because we're going to see that these values change when we look at bromine. So we have chloropropane versus 2-chloropropane. And we found that in propane there were 6 types of primary, 2 types of secondary hydrogens, leading us to expect a 75-25% yields for those. Now in green here, green shows you the actual yields when you run the reaction. So notice that for the primary, from your expected to observed, it's a lot lower. And then for the secondary, it's actually a lot higher. This column here that says ratio of observed yield, we're basically taking the smallest yield, so 45%, and dividing that as the denominator for the other yields. So 45 divided by 45 is 1. 55 divided by 45 is 1.2. So where we were expecting a 3-to-1 ratio, we're actually seeing a 1-to-1.2. So here's a new term for us, relative reactivity. And we defined that by the observed yield divided by the total number of hydrogens of that type. So if you take 45 and divide it by 6, you get 7.5. If you take 55 and divide it by 2, you get 27.5. And now for the last row, we're taking both of those numbers and dividing by 7.5. So for the primary, we get 1. The secondary, we get 3.7. And so that's the important number right there. it's telling us that secondary type of hydrogens with chlorine are 3.7 times more reactive than primary. And ultimately, the reason for that is it is easier to cleave a secondary CH bond than a primary CH bond. So that's clear as mud. What's that?
Why does that happen?
So why does that happen? So remember, you're starting from a carbon that's sp3 hybridized. When you cleave the CH bond, the carbon rehybridizes to sp2. Then the radical exists in the unhybridized p orbital. It happens when you look at the type. So the carbon itself is sp2. Then you can classify it based on how many other carbons are bonded to it. So the more carbons you have bonded to that sp2 hybridized carbon, that stabilizes the radical. And we'll talk a little bit about the name of that stabilization. But tertiary radicals are more stable than secondary, are more stable than primary. So there are these interplaying factors about the stability of the radical you're generating. If we do the same analysis for propane, but now we're using bromine, so the first two rows there, the 6 and the 2, that's the same analysis. You still expect 75-25, but now look at the observed yields. They're much different now. The primary is a lot lower, so it's only 3%. The secondary is a lot higher, it's 97%. Those are the actual yields. If we take 3 as the smallest number, 3 divided by 3, that gets you your 1. 97 divided by 3, that gets you 32.3. Then we take that, and again, that's just a comparison of what you expect in terms of the ratio, 3 to 1. Then the actual observed ratio is about 1 to 32, so it flips quite a bit. The relative reactivity, we take the observed yield, so 3% divided by 6 hydrogens, that gets us 0.5. Versus 97% divided by 2, that gets you 48.5. And then we normalize it by dividing each by 0.5. And now we see that for bromine, a secondary hydrogen is 99 times more reactive than a primary. So we call that reactivity versus selectivity. So we see that when we use bromine, it's much more selective for secondary over primary. So 99 to 1. For chlorine, it was about, 4 to 1? So the question now is, what about a tertiary hydrogen? What's the same sort of analysis? And we'll find that tertiaries are more reactive in general. And then when we look at chlorine versus bromine, it's even a bigger difference then. We do have to change the substrate so that we have a tertiary hydrogen. So for this, we're going to use 2-methylpropane. So there's propane, there's 2-methylpropane. So for primaries, we have 3 equivalent primaries. That's 9 total primaries. There's no secondaries in this molecule. And then we have the 1 tertiary. So that gets us a total of 10 hydrogens. So in terms of the percent, we would take 9 divided by 10. That would give us, we would expect 90% yield of the primary substitution. 0 for secondary, and then 10% of the tertiary substitution product. So we said there were 9 primaries. That's going to eliminate C and D. There were 0 secondaries, so that eliminates A, and then we get B as our correct response here. And so that's telling us we would expect, I'm just going to use X for the halogen. So the 1 versus 2, we would expect D, 90% of that to 10% of the tertiary. So there's the table filling in those numbers. That's, again, our expected ratio. So we're going to run through this now again for the 2-methylpropane, first using chlorine and then using bromine on the next slide. So the same sort of analysis, your expected yield is 90 to 10. What you observe, so let me highlight that in green, 63 of the primary, 37 of the tertiary. If we divide 63 by 37, we get 1.7. 37 divided by itself is 1. So that's quite a bit different than 9 to 1, right? It's about 2 to 1. Our relative reactivity, we take the observed yield, so 63 divided by the number of hydrogens, 9, that gets us 7. If we take 37 divided by 1, that's 37. And then let's divide both of those by 7. So now we find a tertiary hydrogen for chlorine is 5.3 times more reactive. So through this type of analysis, we can see that the trend, tertiary hydrogens react greater than secondary, react greater than primary. So it's telling you, whether it's chlorine or bromine, that's the order that you want to follow. You're going to see that number jump quite a bit when we switch over. We have the same substrate, but now we're using bromine. So same substrate, but now we use bromine. Notice the observed yields. For the primary, it's 1%. The tertiary, it's 99%. And when you run through all that same sort of qualitative math, look how big this number is now. It's 990. So really between chlorine and bromine, bromine is the better reagent to use because it's going to be more selective. As it's more selective, it's pushing you towards a major product and you don't have a lot of byproducts involved. Questions? So let's just summarize this. This is our reactivity order. When we're given a molecule, the first thing we want to do is classify all the different types of hydrogen. Tertiaries, secondaries, primaries, and then we sort of know based on what's there, what the reactivity order is going to be. There are two special cases, allylic and benzylic. We have to remember, if you have a primary allylic, that's going to be more reactive than anything that's tertiary. So keep in mind those positions as well. Our order of reactivity, fluorine was really fast, much, much greater than chlorine. Chlorine was greater than bromine, and those are much, much greater than iodine. So really, we're focused on chlorine and bromine as the synthetically useful ones. Bromine gives better selectivity ratios than chlorine. So we need to explain, considering there are typically less tertiary and secondary hydrogens than primary, why are the tertiary and secondaries more selective than primary? And what's responsible for the extreme change in selectivity from chlorine to bromine? So again, that deals with those mechanistic steps, but also the reaction coordinate. So to build up that reaction coordinate, we'll focus on the two halogens. So we're going to focus on chlorine and bromine, and then we're going to use the table to look at specific types of primary, secondary, and tertiary. So we fill those values in, and then we see how they change for each class of hydrogen versus the halogen that we're using. So the numbers I'm going to write in these entries here, again, they come from that bond association table. So your average primary hydrogen CH, that's plus 421. So we're going to write that value for chlorine and for bromine. So that's what we're keeping constant there. Our average secondary is plus 413. Our average tertiary is plus 400. So again, that right away tells you, if you're, again, starting from 0, what number do you hit first? You hit 400. That's the easier bond to break. And then if we look at HCl, so we want to now form HCl. So the number is going to be negative. That value is going to be constant down that column. So negative 432, negative 432, negative 432. So for HBr, that's negative 366. So that value is constant down that. So again, the type of CH, that's constant for both chlorine and bromine. Then when we look at chlorine, the HCl value is constant. We look at bromine, the HBr value is constant. Now the delta enthalpy change, we're just taking the numbers from those columns and adding them. So this gets us minus 11 for primary, minus 19 for secondary, and minus 32 for tertiary. For bromine, they're all positive, so plus 55, plus 47, plus 34. So if we think about, those propagation steps, we see that no matter what type of hydrogen it is for chlorination, those values are all negative. But for bromine, look at the trend. We're starting again at 0. What number do you hit first? You hit 34 first. So again, the bromine radical, it's going to see that tertiary CH and say that's the easiest to cleave because it takes the least amount of energy. So here are the values I'll put in the table with some colors in. The shades of the green sort of indicate that chlorine's going to do what it wants to do, no matter what class it is. It's not as selective. But for the bromine, you have the green, the yellow, and the red. So the red is the highest energy to get to. So we can plot those numbers in terms of a reaction coordinate to better understand the selectivity again. So I'm showing you a portion of the reaction coordinate. So the reaction coordinate, again, on the x-axis, it's time. So as time proceeds, we're forming the reactive intermediate. Then on the y-axis is your relative energy. Notice that to form the radical, the carbon radical for chlorine, they're all sort of downhill. They're all releasing energy because we calculated those values, negative 11, that was for the primary, negative 19 for the secondary, and negative 32 for a tertiary. So no matter what type it is, they're all releasing energy. Now for bromination, notice that it's uphill. You have to put energy in, and it's easier to get to plus 34 than it is to get to plus 55. So if you imagine, again, that ball has to go up that hill. The easiest hill to get over is the lowest one. If you don't have any tertiary hydrogens in the molecule, it's going to go for the next lowest hill, which is the secondary. So there's our two curves again, chlorination versus bromination. The top of the hill, so when the ball is right there, that's called the transition state. It's typically abbreviated TS. And then it has this superscript with a little dagger, so transition state. One thing I want to point out, again, if you're marching along the x-axis, so this little stick figure here, you're marching along with time. If I draw this line down from the transition state to the x-axis, I hit that point. Notice the top of that hill. There's really not a lot of sort of leeway or spread on the x-axis. When you get to the top of the hill, the ball either rolls back down to the starting material or it rolls to the reactive intermediate. A transition state is very fleeting in time. So its existence is usually less than 10 to the minus 12 seconds. And that, again, makes sense because it's higher in energy. It wants to react and go to something more stable. When you get to a reactive intermediate, so I'll call intermediates exist in wells. So what I mean by that, if you look at this curve here, that's a well. And so within the well, if the ball is in there, it can roll back and forth in that well. So if I draw these lines down to the x-axis, now the time frame is longer. So these are like 10 to the minus 9 seconds. So they exist for a little bit longer. They're a little bit more stable. But again, that's not a whole lot of time. A nanosecond is not a lot of time. So transition states are always at the peaks or the crests. Intermediates are always in a well or a trough. And it does give you an indication of the energy involved for each of them. So the energy of activation, again, that's the largest amount of energy you have to put in to get over the highest part of the reaction coordinate. Any questions? So here is a summary table of radical stability. So pay attention now to the way this is organized. The x-axis says increasing radical stability. So the thing that's furthermost to the right is the most stable. So your primary allylic radical, that's the most stable. So look at that number, plus 369. So again, that's coming from a carbon that's sp3 hybridized. You're cleaving a CH bond, and now you're forming a carbon that's sp2 hybridized, and then the radical exists in the p orbital. So I'm going to draw a line right here. Those radicals all come from sp3 hybridized carbons to start with. To the left of that line, sp2, sp2, sp. The radicals now do not exist in a p orbital. They exist in the type of orbital that the original carbon is hybridized in. And that makes them less stable. So notice the numbers are now higher. For an sp2 hybridized radical, it's 465. That comes from an alkene. If we're starting from an aromatic CH, that's plus 474. If we're starting from an alkyne CH, that's plus 547. That's an sp orbital. So these three are higher in energy, they're less stable. And then as we get into carbons that were originally sp3, they're rehybridized to sp2 with the radical in the p orbital. Basically, as you increase the substitution around that carbon, you increase the stability, and it makes that original CH bond easier to break. So when you're analyzing your starting material, you have to classify them according to these ways, and that's how you're going to choose what gets substituted. Questions? So here's the arrow pushing of, again, how that happens. I'll highlight it in green. You have your X dot radical with the fish hook. So that fish hook means one electron's moving. It's abstracting an H, so one electron moves from the CH bond. The other electron ends up on the carbon. So CSP3 ends up as CSP2, and then the radical is in a p orbital. Now keep in mind the p orbital has two lobes, right? So I'm limited by the drawing of what this is showing you. So there's the single electron, even though it's on this drawing located in the top, really it's in both of those lobes at the same time equally. So it's distributed amongst that p orbital. So meaning that you have a top face and a bottom face. So when that radical reacts, you can get the substitution at the top or the bottom. That's why when you have a secondary radical, it substitutes, you can generate a stereocenter if you have 4 different substituents. So let's see if we can put this into practice here. We have basically a molecule called methyl cyclopentene. So I'll draw it like this. So that's methyl cyclopentene. And of that, I've picked out 3 unique type of hydrogen. So HA, HB, and HC. And the question is asking you to order them in terms of increasing. So increasing bond strength. So the weakest should be listed first, and the strongest should be listed last. So what's the weakest bond? You said A? So let's classify them. C to HA, that's secondary. C to HB is secondary. C to HC, that's called vinylic. So vinylic. So you have HA versus HB. They're both secondary. Is there something special about one of them? So this carbon here is next to the double bond. That's called allylic. So HB is secondary allylic. So that's going to be the weakest bond. So we eliminate A, C, and D. So HB is the weakest, followed by HA, because it's secondary. And then HC is the strongest. Another way of looking at that, HA, HB are bonded to sp3 hybridized carbons. HC is bonded to sp2 hybridized. So no matter what, HC is going to be the strongest. And then once we look at the sp3 hybridized ones, we classify them, and then the HB is the unique one because it's allylic. Any questions on that? So if you were to run a reaction on this, HB is the one that's going to get substituted. That's what it's telling you. Let's consider 2-methylbutane. Two-methylbutane under chlorination. So additions. How many unique sets of hydrogen atoms does 2-methylbutane have? Huh? Is 4. So there's a subtlety to this. It's minimally 4, but it could be considered 5, and you'll see that through this exercise. So we have those primaries are the same. We have a tertiary, so that's got to be different. Secondary, that's got to be different. And then the last is primary. So we have 2 different types of primary, so that's why it's not 3. So minimally 4, but as you'll see through the logic of this question, a better answer probably is 5, because we're talking about unique sets. So which carbon atom, when chlorinated by radical halogenation, will generate a new stereogenic center in 2-methylbutane? So let me just number these, and then you can shout out a number. I'm just going to number it according to the IUPAC name. So those are the numbers for the carbon chain. Again, the carbon 2 has a methyl group. So when you do a CH to Cl substitution on one of those, which one's going to generate a stereogenic center? carbon 3. So let's see how we arrive at that. We'll substitute each one. So if we substitute it at position 1, and we say, is that carbon now a stereocenter? It's no, because we have 2 hydrogens. Let's substitute at position 2. Is that a stereocenter? No, because now there's 2 methyl groups. We substitute at position 3. Now, is this a stereocenter? So yes, you have a chlorine, a methyl, a hydrogen, and then this isopropyl group. So that's 4 different things. So that's a stereocenter. So I'll mark that with an asterisk. If we continue on with the last one, position 4, so that's not a stereocenter because you have 2 hydrogens. So this is our normal way of accounting for uniqueness, right? So 4 unique sets, and then I'm just listing them in descending order of the number. So the 6, the 3 to 2 to 1. So that's that ratio. When we substitute, so I'm gonna put an asterisk by that 2, because that's where we're going to substitute. So that generates a stereocenter, right? So what does that mean? That means you get those stereoisomers, an R1 and an S1. They form in equal amounts, remember, because that lobe has density on the top and the bottom equally. And so if I draw that out here, so there are those hydrogens. If you do the H to Cl substitution, really we could think of that asterisk 2. We could expand the 4 unique sets into 5 unique sets. Because those hydrogens are now different, right? Because when you substitute them for the chlorine, you end up with different products. I'm not sure how much your book talks about this. It does get a little more advanced, but basically we say, in terms of that type of analysis, those hydrogen atoms are called prochiral, because you've done the substitution and it's generated a stereocenter. So if we take that uniqueness analysis one step further, we do that substitution test, we generate an R versus an S enantiomer. So the original hydrogens are prochiral. So let me just check. We'll run through the rest of that sort of analysis, talking a little bit more about chirality. We have some more CH substitution for halogenation reactions under different conditions, different reagents. So we'll be able to finish that on Wednesday, and that's the radical stuff, and probably start the other type of substitution called SN2 and SN1. So coming up to